Dear ladies and gentlemen, my name is Pucillo from the University of Naples Federico II. I will present the results of a study that is part of a more complex research project developed by RFI, the infrastructure manager of the Italian State Railway, and the Department of Industrial Engineering of the University of Naples. In this work, we talk about a special technique, the split sleeve cold expansion, which is fast, cheap, and well known in the aeronautical industry, and that can extend the time required for fatigue crack to initiate near the holes of bolted connection. In this work, the attention is focused on the railway field, in particular on its superstructure, and the presentation is organized as follows. At first, I will try to give you the idea of how fatigue problem is felt on a specific component of the railroad, mainly because of the rapid extension of railway lines in all the world. Then I will show you the details of the preparation of the experimental activity, and we will see how fatigue crack growth rate results have been synthesized for this research. Successively, a preliminary predictive finite element model based on the superposition principle coupled with the weight function technique will be discussed, and the results compared with those obtained experimentally. At the end, the main conclusions and ideas for future activities will be discussed. Rising traffic demand of both people and goods, as well as the transportation of hazardous and non-hazardous materials between different countries, require particular attention for the fatigue design as well as the maintenance planning of railway superstructures. In this slide on the left and on the bottom, we can have a rapid view of the distribution of the main railway lines in Europe and of the train speeds that they can support. On the top right, instead, the freight routes are shown, which are another important productive aspect of the railway transportation. The increase of railway transportation is a worldwide tendency, as we can see from the table reported on the left. This is due at least to four aspects. Railway transportation is able to reach both big and small cities today with more and more reduced time. It's cheaper than the airplane for mobility of people, is cheaper for transportation of goods and people compared to road transport. And the last but not least is characterized by the smallest production of pollution compared to both aeronautical and road transport. This is also a sensible point considered between the goals of Horizon 2020. Just to have a first vision of how many kilometers of track we have around us, this slide shows as an example the railway network in four countries, France, Spain, Germany and Italy. This slide also shows the high-speed line distribution in three countries, just because they represent the real core business of the respective railway managers and that are most susceptible to high security levels because of restrictive standards required for safe transportation at greatest speeds. To have an idea in terms of number, in the bottom part of the slide, we have some number about the kilometer of track and the number of switches. Tracks are periodically checked by instrumented trains, mainly during the night. In the photo on the left, the train named Galileo is shown, which provides to check the rail by means of ultrasonic control. Usually, it gives a warning for a possible point of the track where fatigue crack may exist, and a successive manual check is carried out with the more sensible device, as shown in the photo reported on the right. Moreover, or above all, experience acquired for many years from the introduction of the railway gives to railway engineers the location where fatigue crack most likely may occur. Among them, fatigue fracture originating from bolt hole of rail joints is one of the most common. Rail joints may be non-insulated or insulated. The first ones are progressively changed to continuous welded rail, even if they are still used for temporary repairs. Insulated rail joint, instead, is a necessary component for railway safety because it ensures electrical insulation of two adjoining track sections for signaling purposes and provides a tool to detect broken rail. Moreover, they give economic advantages for substitution of track segments submitted to accelerated wear, for example the curve. However, insulated rail joints are submitted to severe loading conditions that can cause fatigue cracking at the whole surface. This is due to high well track impact forces and reduced flexural stiffness than conventional rails. Moreover, a stress concentration is introduced because the presence of the hole. Considering the great increase of a railway line to extend the fatigue life of the insulated rail joints, but also of other drilled components of the railway infrastructure, cold expansion process, which is a technique capable of inducing residual compressive stresses in proximity of the hole, has been chosen by RFI as a possible remedy to increase the time required for fatigue crack initiation on the whole surface, and so to extend the inspection interval. With this technique, an hole is expanded along the radial direction by pulling an oversized taper mandrel. This produces a ring of material near the hole where the hoop residual stress are negative, which is believed to improve fatigue strength of insulated rail joints. However, cold expansion is well known in the aeronautical industry, and almost all the studies deal with aluminum. No experimental studies exist on the cold expansion effect on the fatigue strength of railway structural steels. For this reason, RFI and the University of Naples decided to investigate on the effects of this technique on railway steel by means of an extensive testing campaign. Rectangular drilled specimens, whose dimensions are reported in this slide, were extracted from a specific batch of rail. Before drilling the specimen, a stress relief heat treatment was executed with the aim to remove all existing residual stresses induced during the rail production and to be sure that the only parameter affecting the fatigue crack growth rate was the residual stress field due to cold expansion. For the same reason, the surface finish has also been treated with detail with the 3 steps of diamond grinding and, at the end, one tangential grinding. In this slide, we report some photos concerning the cutting and the drilling sequence and the stress relief cycle. Cold expansions were performed in FTI Seattle, but all the photos made during the process are under a confidentiality agreement. At this point, two types of crack gauge were applied on expanded and not expanded specimen, and a crack gauge adapter was used to insert the crack gauge into a common Whitson bridge. Two load levels were chosen for the fatigue test, 219 and 400 megapascal, with a loading ratio equal to 0.05. Data acquired by crack gauges are reported in this slide for both load levels. it is found that for cold expansion degree equal to 2%, the fatigue life increase of about 50% to 100%, whereas with cold expansion equal to 4%, an increase of about 200% is found. This is a very important result in the railway sector, in particular for the extension of the fatigue life of rail and bolt hole, which is not present in the current literature. Successively, to calculate the stress intensity factor range, delta K, at a specific crack length measured by crack gauges, two geometries, two cases were considered. Indeed, in some tests, only one crack started on the whole edge, and this was true for almost all the fatigue life of the specimen, as shown in the top left diagram. In this case, the darkened part of the graph was excluded, and we considered a single crack geometry. In other cases, instead, it was possible to consider a double symmetrical crack, but for both cases, the Bowie solution was used to evaluate the stress intensity factor. The crack growth curve have been obtained by the incremental polynomial method as recommended by the reference standard. This technique was preferred with respect to the secant method since the curves obtained by it have a more regular trend. And at this point, starting from the data acquired with the non-expanded specimen, the parameters of the Foreman curve have been extracted with MATLAB for the specific loading condition adopted for the experiments. Once the parameters of the propagation law for the non-expanded specimen were evaluated, it was decided to proceed as follows to predict the propagation curve of the expanded specimen. By linear superposition between the stress intensity factor due to the applied load and the residual one due to cold expansion, the actual delta K is calculated, setting kappa minimum equal to 0 if it is negative. Then, using the parameter of the Foreman's law, we tried to predict the crack growth rate for the expanded specimen. The stress intensity factor due to residual stresses induced by cold expansion has been evaluated by means of the weight function, given by Wu and Carlson and Glinka for crack length smaller or greater than 6 mm, respectively. And the great utility of the weight function is due to the fact that once determined for a specific geometry of the cracked body, it is possible to calculate through a simple integration the stress intensity factor due to any applied load. It is enough to integrate the product between the weight function and the distribution of the stresses acting on the plane of the crack. This latter stress distribution must be calculated in the uncracked body. For this purpose, a finite element model was realized to predict the residual stresses induced by cold expansion. Therefore, the effective stress intensity factor due to exercise loads and residual stresses has been estimated by means of a superposition technique. The results of the predictions and their comparison with the experiment are shown in this slide for a cold expansion degree equal to 2%, whereas the results concerning 4% of cold expansion are reported here. For both cases, it is found that the predictive model overestimated the cycles to rupture by a factor of 2 or 8 in the worst case, which is very consistent with the literature. And the higher predicted crack growth rates suggest the probable inadequacy of the models based on the principle of linear elastic fracture mechanics. And, in fact, a first finite element model is under development that is able to contemplate phenomena of diffuse plasticity, which constitute the natural continuation of the analysis carried out in this work. Let us now move to the conclusion and the future works. An experimental campaign has been conducted on expanded and not expanded specimens extracted from railway rails, adopting the two load levels and the two degrees of cold expansion. All the specimens have been submitted to stress relief heat treatment and to an accurate surface finish treatment to be sure that the only parameter affecting the fatigue drag rate was the residual stresses due to cold expansion. 2% of cold expansion give an increase of the fatigue life of about 15 to 100%, whereas with the 4% of cold expansion, an increase of about 200% is found. Data acquired by crack gauge have been analyzed and synthesized, and starting from those concerning the not expanded specimen, the parameters of the propagation law proposed by Foreman have been evaluated. Then, for the expanded specimen, fatigue drag has been simulated using a finite element predictive model based on the superposition between the stress intensity factors calculated with the weight function and concerning the residual stress field induced by cold expansion and the one generated by the external loads. It is found that the predictive model overestimated the cycles to rupture by a factor of 2 or 8 in the worst case, which is consistent with the literature. However, this suggests the inadequacy of models based on the linear elastic fracture mechanics, and indeed a first finite element model that is able to take into account diffuse plasticity is now under development.